Okay, so we're going to start looking at similar polygons. Before we get to that, we are going to need to review how to solve a proportion. We just kind of did one when we went over the homework, but if two ratios are equivalent, so a ratio is just a number over another number, so like this is a ratio, this is a ratio. If they're equal to each other and written in an equation, then that equation is called a proportion. So solving a proportion involves solving something that looks like this, basically two ratios set equal to each other. Okay, so I'd like you to solve this one, and when you solve it, then explain your steps in words to the best of your ability. Remember how we did that homework that we went over. What's your first step going to be? Cross multiply, exactly. And I will tell you this comes out to a decimal, so don't think you did it wrong if it comes out to a decimal. Okay, so when we cross multiply, we're going to do 6 times 4 and get 24. And 5 times x and get 5x. Now, the second step, what did you write as your second step? After cross multiply, then what? Okay, but this is actually a step right here. When you cross multiply, what do you do with those numbers? What did we do with the 24 and the 5x? What do we do with them? Yeah, you have to set them equal to each other. That's actually a really, really important step that sometimes people forget. They know cross multiplication and they cross multiply, and then they're not sure where to put the equal sign, especially in problems that become a little bit more involved. So it's really important that we remember that cross multiplying involves creating an equation. You have to have an equal sign in there. So I'm going to say set cross products equal to each other. Cross products are the numbers you get when you multiply across, right? Equal to each other. Okay, then you're saying we divide. That's what you said you put as your next step. That's true. In this problem, we have to divide. In general, what are we doing? Yes, question? Okay, so the question was congruent. That things are congruent. Numbers are equal. So like if you had a ruler and another ruler, you could say they're congruent to each other because they're things. But these are actually just numbers. Equal. Yep. So it's an equation. Okay. So when we get to this point, we have 5x equals 24. We have to decide what to do with the ultimate goal of doing what? Solving for x. We're basically solving for x. That's what your next step is going to be. Solve for x. Now, in this case, we had to divide both sides by 5, right? But sometimes there might be a different way that we have to solve for x. So you have to just remember that once you get the cross products equal, then you're solving. And this turns out to be 4.8. Okay, so that's called the cross products property. In a proportion, the cross products are equal, so we cross multiply and solve the resulting equation. Why does it say B, this is like A over B, this is the general case, right? A over B equals C over D, where B and D cannot be 0. Why can they not be 0? What they're calling B and D. Well, what is A over 0 equal to? Undefined, exactly. It's not equal to 0. It's undefined. You cannot have the fraction, denominator of a fraction equal to 0. It's literally undefined. It's like saying dividing something into 0 equal parts. That's impossible. You can't divide something into 0 parts, right? So remember that the denominator of a fraction can never be equal to 0, okay? All right, so when we get to a little bit more complex proportions here, we have to remember to distribute and put anything that's not one term in parentheses. So this first equation here, 15 over x plus 1, I'm going to put this x plus 1 in parentheses. So we're going to do 3 times parentheses x plus 1 equals 15 times x. The important part of the parentheses is that it helps us to remember that we have to distribute now. So this is 3x plus 3 equals 15x. So solving for x involves distributive property. What are we going to do next? Jake? Okay, we can't divide yet because we have this little leftover thing here. So we have to actually collect all the x's together. Subtract 3x on both sides. Because we need to get it so that all the x's are on one side. So we get 3 equals 12x. And what does x equal? Don't say 4. Or 1/4. It's not 4. It's 1/4, right? 3 equals 12 times x. We have to get x by itself, so we divide both sides by 12. This is why showing your work and actually not taking shortcuts sometimes prevents some mistakes. Sometimes people see 3 and 12 and they just think 4, but you got to remember if it's 3 over 12, it's actually 1/4 or 0.25. Okay, let's look at part B here. Again, we've got some binomials, some multi-term expressions here. So when we cross multiply, we get negative 12 equals x minus 5 times x plus 3. How do we handle that? What do we have to do? Distribute, and you distribute everything. You may have heard it called FOIL, right? First, outside, inside, last. X times x is x squared. X times 3 is 3x. Minus 5x. Minus 15. Combine like terms. What's negative 5 plus 3? Yep, good. Negative 2x. Okay, how are we going to solve this problem for x? It looks a little complex to me. I don't know what to do. Add 12 to both sides. Good. Then what? Factor. Exactly. 0 equals, and we have to remember to set it equal to 0 before we can factor. Anytime you have an x squared term and an x term, it's going to be factoring. So negative 15 plus 12 is negative 3. So this is what we're factoring. You guys go ahead and factor that. Okay, so what multiplies to be negative 3 and adds to be negative 2? X minus 3, x plus 1 equals 0. So what does x equal? X equals 3 or negative 1. Perfect. Now, we should be able to plug that back into our original equation. We had x minus 5. So if we're going to check whether 3 works, 3 minus 5 over 4 equals negative 3 over 3 plus 3, right, where we're plugging in our value of x. What's 3 minus 5? So this becomes negative 2 over 4, and this is negative 3 over 6. 3 plus 3 is 6. When you cross multiply, you get negative 12 equals negative 12. And that checks, right? You could do the same thing with the negative 1. Plug it back into the original. Negative 1 minus 5 over 4 equals negative 3 over negative 1 plus 3. Well, that's negative 6 over 4 equals negative 3 over 2. Again, cross multiply, you get negative 12 equals negative 12. And it checks. Right? So all of your solutions, whatever you get for x, should be able to plug back in. Okay, so this next word problem can be solved using proportions. It can probably be solved without using proportions, but we want to set it up as a proportion because it's important to understand how to do that. Sometimes they're going to give you word problems where it's not something you can do without a proportion, so you want to make sure you know how to set it up. Okay, Ella is reading a map with a scale of 1 inch equals 20 miles. Right? 1 inch equals 20 miles. So you want to set that scale up as a ratio, 1 inch to 20. You understand what this means, right? On the map, 1 inch on the map is 20 miles in actual distance, right? So this is map over actual. Yep. Okay, on the map, the distance Ella drives is 4.25 inches. So we have to decide, does that go on the top or the bottom? On the top, because we're talking about the map and we're talking about inches, 4.25 inches. So we're just going to put x on the bottom because we're trying to figure out how many miles this is. So this now just becomes cross multiplying and how many miles does this turn out to be? 85 miles exactly. Does everybody have a calculator on them? If you need one, come get one. All right, so the second part B of this lesson is talking about similar polygons. So similar polygons have the same shape, but not necessarily the same, what do you think? Size, exactly. This little squiggle is the symbol for similar. Remember, congruent sign was an equal sign with a little squiggle over it. Well, similar is just the squiggle. Okay, so think back when we did transformations. What was the transformation called? The one that changed the size of the figure. Dilation. Good. Very good. So with a dilation, the pre-image and the image are actually similar figures. So they weren't congruent anymore, right? They changed size. So that's when we can say they are similar figures. So if we take well, it's not letting me, but I'll just draw one myself. I was trying to get a nice one there, but if we take a figure like this, and let's clone that. Okay, and let's shrink it. Okay, this one. Okay, so these are two similar polygons, right? The same shape, but not the same size. What can you tell me about the lengths of the sides of these polygons compared to each other? They're reduced, right? They get smaller, so they're not the same length. No. So not congruent anymore. What about the angles? That angle the same? That angle the same? Aha. So, similar figures have, good. So by definition now, two polygons are similar if corresponding angles are what? Congruent. Good. And corresponding sides, are we going to say congruent here? No, they're not congruent, but they actually all grow or shrink, right? Enlarge or reduce by the same ratio. The scale factor is the same. So we're going to say the sides are proportional. They're in proportion with each other. Same ratio. Same scale factor. All of this means the same thing. How's this different from two polygons that are congruent? Corresponding angles are what in congruent polygons? Congruent, and corresponding sides are also congruent, right? In congruent polygons, sides and angles stay the same. They're like identical figures, right? So sides are congruent as well in congruent polygons. So with similar, the sides are going to be a different size. So just like with congruence, we had congruent statements. With similarity, we have similar statements, similarity statements. And it basically looks like this. And you're saying, right, ABCD, polygon ABCD is similar to, there's that symbol, is similar to GHIJ. When we talk about corresponding angles, what angle corresponds with angle A? G. How do you know that? Okay, so you can look at the diagram, and you see they're both right angles, they're marked the same. How can you tell that from the similarity statement? Yeah, because the order of the letters tells you the correspondence. So since A is the first letter and G is the first letter, A must go with G, right? So we're going to just write right here, order matters. So we have A is congruent to G because they correspond. B is congruent to H. Like we said, all of the corresponding angles are congruent. This is what's a little different from when we did congruent polygons, right? Now they're showing us the ratios. They're saying side AB and side GH correspond with each other, and they're in the same ratio as BC and HI. And they're in the same ratio as CD and IJ and AD and GJ, right? So you can figure out what the ratio is and check if they're the same to determine if things are similar. Okay, we have to watch our order. When have we seen this before? When did we have to watch our order before? When we were writing what kind of statements? Congruent statements, right? So it's the same idea. You have to just look at the correspondence. All right, so in this part, they're asking, are these two polygons similar? Based on our definition, all the sides have corresponding angles have to be congruent, and corresponding sides have to be in the same ratio. So in order to determine if these two triangles, in this case, are similar triangles, we have to check the angles, and we have to check the sides. So let's do angles first. Are the corresponding angles congruent? Yes, you have a single slash here, a single here, a double here, a double here. Every angle has a matching corresponding congruent angle. So, corresponding angles, congruent, check, right? That piece of it we can check off. What about the sides? So we have to check all of the ratios of the sides. So again, we have to be careful that we're using corresponding sides. My little advice and tip for you when it's triangles, there's only 3 sides. So you can label small, medium, large, right? There's always going to be a smallest, a largest, and the one in the middle. If you do that on both of these, right, 10 is the smallest, 15's in the middle, and 20 is the longest. If you do that on both triangles, then you automatically can see what corresponds with what. Small goes with small, etc. So what is the ratio of small to small? 8 to what? 10. If we simplify this fraction, and you should always, always, always simplify fractions from now until the rest of your life. If there's a fraction, you should simplify it. Okay, so yes, this should be 4 over 5. Let's do medium to medium. Does it matter whether I do 12 over 15 or 15 over 12? Yes. Okay, so yes and no. Because since I already started with 8 over 10, then I have to do 12 over 15 because I put the smaller one on top, the first in my, small to small, so I have to do that same order when I'm checking the rest. Had I started with 10 over 8, that would have been fine, but then I would have to have 15 over 12. Right? So you just have to make sure you stick to the same order. Whether you're considering it getting larger or getting smaller doesn't really matter, but you have to make sure you go in the same order. So 12 over 15 simplifies to 4/5. Top and bottom gets divided by 3. Good, and then we do large to large. What over what? Good. 16 over 20, which simplifies to 4/5. So are the 3 sides in the same ratio? Yes. Are they similar? Yes. So corresponding sides are proportional. Wow, I'm having a hard time writing this here. So we can check that off. Similarity statement, triangle, ABC. Similar to triangle. Now watch the order. ABC. A is the double arc angle. So what goes with that? D, good. And then E, and then F. And our scale factor we found to be 4 over 5. Again, if you had gone the other direction, it would have been 5 over 4 as the scale factor, and that would be correct as well. Okay, so the last part of this lesson is actually going to be proving triangles similar. Yes, proofs, exactly. Yay! Yay! Okay, so in this box is some space that I want you to just kind of recap what I just taught you. 2 polygons are similar if there's basically 2 criteria. Write it down in your own words. Okay, so you're going to want to mention the 2 important pieces of this concept here. 2 polygons are similar if corresponding angles, good, are congruent, and the corresponding sides are proportional, or you can say in the same ratio, or have the same scale factor. Any way you want to say it, you want to make sure it's basically congruent for angles, but ratio or proportion for the sides. Okay, this is a new theorem that is going to become applicable to this concept. It's called the third angles theorem. And I'm going to see if you can figure out what the theorem says. So we'll start off together. If you have two triangles and A is congruent to D, so A on one triangle is congruent to D on the other triangle, and B is congruent to E, again one from each triangle, what do you think you can conclude about the third angle? Okay, why? Why does that make sense? Yeah? Aha. So, since all three angles add up to 180, then when we add B and A together, since they're the same as E and D, we'll get the same number. So what's left over to get you to 180 has to be the same in both cases, right? So explain that again in your own words. Okay, so you might want to mention triangle sum theorem here. A plus B plus C is 180, D plus E plus F is 180. You don't have to write this exactly, but however you described it, you may have even used numbers, like if this is, 10, and this is 80, and, well, B is the same as E, so that's 10, so that's 80, then this would have to be 90, of course it doesn't look like 90, and this would have to be 90, because in order to get to 180, that's the only way to make the numbers work. Okay, so think back now when we were learning about congruent triangles. And the lesson was very similar, no pun intended, to this one. But we learned about, in general, congruent polygons. Then we started talking about, okay, let's focus on triangles. And we said if we want to test if two triangles are congruent with just the definition, right? The definition said all the angles are congruent, all the sides are congruent. So the first couple of examples we did in that lesson, we said, okay, in order to answer the question, are these two triangles similar? Can you not do that, please? You're literally going to break that. Okay. Then we have to check, does every angle have a corresponding congruent angle? Does every side have a corresponding congruent side? And we said we really have to check 6 pairs of parts, right? We have to check 3 pairs of angles and 3 pairs of sides. And there were 6 pairs of parts. We said, okay, look at all of 6. If they meet the criteria, then the triangles are congruent. But then what happened? By the time I gave you your test, and the question said, are these two triangles congruent? Were you checking all 6 pairs of parts by that point? How are we determining if triangles were congruent by that point? So you were checking all 6 parts then? All 3 sides and all 3 angles? Okay, you were looking at the congruence marks. And what were the choices of how you could prove triangles congruent? Good. ASA, SAS, SSS, HL, AAS, right? We had 5 ways. We basically said, well, actually, we don't have to check all 6 pairs of parts. We really only need 3. Not any 3. There were only some that worked. But it was like a shortcut. If we just know sides, SSS postulate works. We don't need to know angles. Right? If we know 2 sides and the angle between them, then that worked. Right? We didn't need all of the 6 parts at once. So the same thing is going to happen with similarity. In order to prove 2 triangles are similar, you actually don't need to check all the angles and the proportionality of all the sides. There's shortcuts. Okay? So the first shortcut is called AA similarity postulate. What do you suppose this is going to say? The hint is in the middle here. If S is congruent to M and R is congruent to L, then what do you think we're going to conclude here? Okay, well that was the third angles theorem. This is the AA postulate. What are we trying to prove here? Then what? And the triangles are similar, right? So triangle RTS is similar to, right, little squiggle, triangle, you got to watch your order, right, RTS, LPM. Good. So how would we state this in words? If what? All right, so let's just what kind of angles? Okay, if two pairs, right, it's not just two angles like one here and one there, it's like two pairs, oops, if two pairs, forgot the two, of corresponding angles on two triangles are congruent, then the triangles are similar. Good. So why is this not called the AAA postulate? How come we don't need to know all three? Yeah, the third angles theorem basically says that if you know two, the third one's going to be anyway, so we don't really need to call it the AAA postulate because we really only need two angles at a time. So why don't we need to know all three pairs? Because of the third angles theorem, basically. Okay, so here's some examples. Are the two triangles similar? Explain how you know. List any theorems that help you find necessary information. So in the first one here, they give us that this is 45 degrees, and this one is 45 degrees. Does that make them congruent? Yeah, same measure means they're congruent. Good. So we've got vertical angles also. So, are these two triangles similar? By what postulate? Good. Yes. By AA, and you have to write the little squiggle. AA similarity postulate. It says list any theorems that help you, so let's say vertical angles theorem we used, right? All right, what about number 2? I want you guys to figure out if, I'll have you do 2 and 3. You're going to need to find some missing information in these diagrams to be able to determine if the triangles are similar. So give those a try. Okay, so since they're not telling us that the triangles are similar, we don't know anything about congruence here. We have to use triangle sum. So what is the missing angle? What's angle K going to be here? 80 degrees, because 30 plus 70 is 100, so we got 80 degrees left right there. Now, in the second triangle, we've got 70 and 85. What's angle P going to be? 25 degrees. Are these triangles similar? No. Why not?
Because the triangles on the United States that
Okay, there's really only one pair of congruent angles, right? And we need at least two for the AA similarity. All right, number 3.
yes, they are.
Good. The missing angle here is 51, and the missing angle there is 39. So they are congruent, yes, by AA similarity. Any questions on AA similarity? So you can imagine in a proof, right? You just need to show two pairs of angles are congruent, and you can conclude that the triangles are similar. How many arrows would point to our statement that says triangles are similar? 2, because this angle is congruent to that angle is congruent to that angle. 2 arrows would point. We're not going to do proofs today, but just like you to think ahead a little bit. Okay, the next shortcut is called SAS, similarity. Be careful to put the squiggle there because we did have an SAS congruence postulate. This is SAS similarity. There's a difference. Okay, so this says AB is to QR as AC is to QS. Now, there is not an official way to mark your diagram with like what corresponds with what. But with these types of problems where we're trying to figure out if triangles are similar, I kind of made up my own. So it's not official. You won't see it in the book. You won't see it on worksheets, but I find it helpful. And so when I see AB is to QR, I like to mark them like this with a squiggle and a squiggle. And it just shows me that those are the two that kind of correspond with each other. It's not a congruence mark, right? Clearly they're different sizes. And it doesn't really make sense to say this one is similar to that one. That doesn't really make sense because similarity involves comparing ratios. You can't just have one ratio. So that's why there's not a technical way to do it, but I find this helpful. So AC then is to QS. I just do a double squiggle on both of those. Well, we're not going to mark that one because this is the SAS postulate. So it's trying to show us that we only need 2 pairs of sides that are proportional. And which angles do we need? It's called the SAS postulate. Yeah, so how would you describe that angle in relationship to the sides? So how would you describe where that angle is in relationship to where those sides are? Can it be any old angle? Can it be any 2 sides in any old angle? Right, it's in between the proportional sides. What was the word for that? Okay, but well, there's really 3 vertices though, right? So there's a vertex everywhere. This was called the included angle. Remember the included angle? But you could call it the angle in between the 2 sides. That's fine. Okay, so if this is the situation, 2 pairs of sides are proportional. We can write a true proportion about them. And the angle that's included between them are congruent, then the triangles are similar. So triangle ABC is similar to triangle QRS. So how should we write that in words? If 2 pairs of corresponding sides, not similar. It doesn't make sense to say sides are similar. What's the word we're going to use here? Are proportional. And the angles between them are congruent, then the triangles are similar. Okay, so Are the triangles below similar? If so, why? Well, notice these triangles are overlapping. Okay, so notice these are overlapping triangles. Let's draw them separately. This is K, L, P, and K, M, N. Now I'd like you to label your triangles that you've drawn separately. Label them with the lengths of the sides. Be careful. Lengths of the sides. We've got KP is 12, LK is 8. Now if you go all the way K to N, we've got 12 plus 3 is 15. And then MK is 8 plus 2, which is 10. So now we can check the ratios of those corresponding sides. So LK corresponds with what? MK, right. So we've got 8 is to 10. Simplify that, and what do we get? Now we'll do KP. KP is to, so 12 is to what? 15. What does that simplify to? 4/5. Is this enough to say that they're similar?
Yes. No.
That's only two sides. What else do we need to check? The angle between those two sides. What angle is between these two sides? What angle is between these two sides? These two sides and these two sides. It's the same angle, right? So angle K is congruent to angle K by reflexive property. Remember, anytime you have overlapping triangles, you're looking for maybe a reflexive in there. So are these two triangles similar? Yes. By SAS similarity. So watch your order now. I could say triangle LKP similar to triangle MKN. Good. Okay, the last one is the SSS similarity postulate. And it basically says you don't need to know anything about angles. If all three pairs of corresponding sides are what? No, we can't say sides are similar. Good, proportional. Then the triangles are similar. So you don't really have to know anything about angles. In this example, we would just be checking all three pairs of sides. Again, small, medium, large, I think is helpful. Small, medium, large. And you're just going to check small to small, medium to medium, and large to large. There's no shortcuts. In other words, you can't do small to small and then medium to medium and say, oh, well, they're the same, so the last one must be also. Because that's not necessarily true. You could have two triangles that have two pairs that are proportional and the last side is not proportional. So you really need to make sure you're checking all of them. So small to small would be what? 6 to 9, which is 2/3. Medium to medium is 8 to 12, which is 2/3. Large to large is 10 to 15, which is 2/3. Are they similar?
Yes.
Yes. Remember to put the squiggle. SSS, similarity. You gotta put the squiggle. Similarity statement, you just have to watch your order. STU, similar to, triangle. Be careful now. We don't have angles to look at here. S is between the longest and the shortest. So what goes with that on the other triangle? I started with S. I started with S. Okay, I started with S, and that's between the large and the small. Which angle is between the large and the small sides? X, right? Here's small and large, so X comes first. Then I went to T. T is between small and medium. Which one's between small and medium? V, and then W. Okay, so in conclusion, there's 3 shortcuts, bless you, to proving triangles similar. We didn't get to practice too many of these here, but I just want to do one together. We have a couple minutes here. Go to the practice and part B. In this section, they're actually telling you these triangles are similar. So read your directions carefully, because sometimes they're going to say, are these triangles similar? And that's when you're testing the postulates. But if they're saying to you, these are similar, then you know that all the sides are proportional. And they're going to ask you to solve for missing variables. So in this case, we have x minus 2. And what is the corresponding side to that on the 12, right? So you're going to be writing proportions for this. Now I just need another side from this smaller polygon. 18, and that goes with 24. Could I have used 27 and 36? Sure, that should work. Now 18 over 24, remember I said simplify any fractions you can? That goes for even, just give me a second here, okay? Even this, right? They can both be divided by 6, so this becomes 3 over 4. Cross multiply. Isabel, I didn't give you your homework yet. Sorry. Ugh. All right, so when we cross multiply, we got 4 times x minus 2 equals 3 times 12, and we solve the proportion from there. Okay.